Okay, and now for Lyapunov functions. So we have a system of differential equations. Y of t is a solution curve. So a function is a Lyapunov function of the system if there's a region of the domain where the gradient of L dot F does not change sign. So what that means is that the gradient of L and the vector field F always either have an angle between 0 and 90 degrees, right? Because then the dot product would be positive, or between 90 and 180 degrees, and then the dot product would be negative. So it's a curve where the gradient and the function are always pointing in the same direction or in opposite directions. Explicit Lyapunov functions are hard to find, especially if you want to find one that covers the entire plane, but you can build some locally. A Lyapunov curve, and again, that's not standard notation, that's just what I call it. This is a curve for which all the solution curves cross in one particular direction. Null-clines are good examples of that. If we think of null-clines as curves connected by equilibrium. So Lyapunov curves trap solutions in some sense. So we'll look at three examples. We'll look around the equilibria 18,0 and, oops, that's not 18,0, that's supposed to be 0,18. And 12,0 in the competing species model. Here's the model again. And we'll also look at the line x plus y equals 20. And we had some information about the equilibria, which is here, which we will use in a bit. So, where'd my tablet go? How do we go about looking at this? So for the line, we'll start by looking at the line x plus y equals 20. So this is a line in the plane. It's got x-intercept 20, y-intercept 20. The vector along here is, the direction vector of this line is minus 1, 1, or 1 minus 1, depending on how you want to think about it. You go down 1 and over 1, and that gets you the slope. So what's a perpendicular vector to this? Well, you switch the components and drop the sign on one of them. So 1, 1. We think of the vector 1, 1 as being positioned along that line. So there's our function, is our vector field is 12x minus x squared minus xy, comma 18y minus y squared minus 3xy. So what is the dot product between the function and this normal vector, this perpendicular vector to the line along that line? Well, you take f dot w, and that'll be 12x minus x squared minus xy dot 1, because this is w, times 1, plus 18y minus y squared minus 3xy times 1. But we want it along this line, so it means replace all the occurrences of y by 20 minus x. Because if you solve that for y, that's what you get. And I'm not going to punch that in here and grind it out. It's a lot easier just to do that on the computer. So we will go to GeoGebra. So this is our slope field for our vector field for our competing species. We had in equilibrium at 0, 0, one at 0, 18, one at 12, 0, and one at 3, 9. Okay. And we know that The y-axis consisted of solutions, right? Going down here, going up there, and we know the x-axis consisted of solutions going towards the equilibrium at 0, 0. No, going towards the equilibrium at C at 12, 0 for positive values of x. And now our line is that. That's x plus y equals 20. And so that's a line. It doesn't have anything to do with much of anything. But the point is if we can calculate the dot product between the vector field and the vector 1, 1, which points off up here to the right, if we can calculate the dot product between that, and if that dot product is always of one sign, then we know that the solution curves have to cross it in one direction. And so the easiest thing to do is just to go over here. Here's my x component, here's my y component, and we say, well, if x is between 0 and 20, take the dot product of 1, 1 with the vector field f comma g, and what do you get? You get f of x 20 minus x plus g of x 20 minus x, and you can plot that, and there's that plot. And that's always negative, right? So we take the dot product between the function and between the vector field and the normal curve to this line, and we got that that's always negative. The vector that's normal to this line is 1, 1, that points up to the right. That means all solutions, if they cross this line, they cross this line going from the upper right down into the lower left. So in particular, since we know that this solution here on the line on the y-axis, and we know that the x-axis is also solutions, what does that mean about our system? Well, if you enter into this triangle bounded by x plus y equals 20, the x-axis and the y-axis, you cannot leave, right? Your solutions go in here and they can't leave. And that helps a lot in dealing with these sort of constructions of trying to figure out what's going on with vector fields. And so you can take these sorts of lines and just sort of get a boundary condition on, what has to happen. All the vectors on this line point down into the left, and so all solutions have to cross, and some of them go up to B and some of them go down to C, as we know. Okay, so let's go back to our curve. And so let's see about what happens at the equilibria. So at the equilibria, at 0, 18, we have an eigenvector pair of -6 and -18, -2, 9, and 0, 1. And at 12, 0, the eigenvector pairs lambda 1 equals -12 and 2, 1. So at 12, 0, so what do we know? What do we want? We want small circles centered at 12, 0. And I want the page down here. I've run out of page. Oh, but I don't want the footer. Okay, I'm going to pause this while I figure out what's going on here. Okay, I think I got my stuff straightened out here. So what are small circles centered at 12, 0? So a circle can be represented as a center plus r times cosine t sine t. That's the parameterization. In vector form, the parameterization would be x of t comma y of t equals the center, in which case 12, 0 plus your radius cosine t sine t. So there's a circle of radius r. Centered at the point 12, 0. And so that's the parameterization that we want. What's a vector that's perpendicular to this? Well, we know we've got a circle and a parameterization, and we know that the vector x prime of t, y prime of t is tangent to the circle. And in this case, x prime of t is equal to minus r sine of t, and y prime of t is equal to r cosine of t. So a perpendicular vector is, well, take these two components of my tangent vector, switch them, and change the sign on one of them. Right? And so this vector is perpendicular to this vector, and you can check that just by taking the dot product between the two. And in this particular case, this vector is actually the vector that points out from the circle. It's the perpendicular vector pointing out. So we want f dot perpendicular vector along the circle. And you do that the same way we do before, we did up here, right? Here's my x component. Replace all the x's with 12 plus r cosine t. Replace all the y's with r sine t, and then take the dot product with this thing. And that would give us f dot, the perpendicular vector, along the circle. And if that is always less than 0, implies that here's our circle, right? If that's the perpendicular vector, if the f dot perpendicular is less than 0, then that means my function has to be pointing inside. In fact, the vectors are pointing inside everywhere on this circle. And what that means is, of course, once you go into the circle, you can't come back out. You have to go to the equilibrium that's inside there. So if we go back to GeoGebra, let's see, let's turn this off. Oh, no, we want that, but we don't want this one. Let's get rid of that. So C here is my circle at 12, my equilibrium at 12, and there's a circle of radius at this point, 0.536. So the slider A is being my radius. So we're looking at circles centered at that point. And we want to know, are the vectors, the vector field pointing inside of that circle or not? If they are, then we know that once you cross one of these circles, once you cross that circle, you're trapped and you have to keep going in. So how do we actually deal with that? Now that we've done this one, we can just delete that and we can zoom in some so we can actually see what we're doing. Oops, I'm going to need to readjust some stuff. So let me pause again. Okay, so this function p of t here is from 0 to 2 pi. Here's our parameterization. We want to plug into the f component, the x component of a vector field and the y component of a vector field, and take the dot product with our cosine and sine. So what does that look like? Oh, well, it looks like that. And we'll shrink this out so that we get a better view of that. Right, 2 pi, this is one cycle, once around the circle, it's always negative, right? And if we let that pi go, it's very big. And then if we let it decrease from 1 towards 0, what we see is it gets closer and closer to 0. So this is the dot product between the outward pointing circle and the outward pointing normal of the circle and the vector field. And as we go from 1 down towards 0, the magnitude of it is decreasing. That's why it's creeping up towards the 0 axis. But you notice that it's always negative here. And as it keeps creeping up, it's still always negative, even as it gets very small. And you can show that it actually is always negative as long as you have a non-zero radius as it goes in. And we'll shrink that then. So what that tells us then, if we come back here and we look at these circles around 12, the vector field always points in. And so therefore the vectors are trapped by those circles. And so those kind of circles are very useful things to deal with. Now, let's see, let's go back to a Word document. What about ellipses? So I'm going to go up and grab something that I want. This piece of information. So at 0, 18, what do we have? The 0, 18. My eigendirections, -2, 9 is like that. And we're going in here. Lambda 1 equals -6. And 0, 1, that's in this direction, with lambda 2 equals -18. This is a very strong flow in this direction because it's got a very high eigen value. And then it gets very close to this before it converts and goes in. And so circles aren't super good here because no matter how small I make a circle, there's still going to be somebody coming in and just going out a little bit there. So instead of circles centered at 0, 18, let's do ellipses. So if we think about what an ellipse is, right? If we think about an ellipse, you can think about it as something that looks like this. It's got one vector that points out in this direction. We call that vector v1. It's got one vector that points out in this direction. We can call that vector v2. So an ellipse center of the origin would be cosine t times the vector v1 plus sine t times the vector v2, right? When t is equal to 0, you're here. When t is equal to pi over 2, then this term is 0, but that term is 1, so you come down here. When t is equal to pi, this is -1, this is 0. That brings us down to this side and then back around, back around. So that's the basic idea of how to center an ellipse centered at the origin. If we want an ellipse centered at 0, 18 with the eigenvectors as the vectors, then we would want cosine t minus 2, 9 plus sine t 0, 1 plus the center, which is 0, 18. And if we want to be able to vary the size of it, we can multiply both those terms by r, and that would shrink it and expand it. And so that gives us a parameterization x of t equals minus 2r cosine t, y of t equals 9r cosine t plus r sine t plus 18. So that means we have a nice ellipse centered at 0, 18 with these as its primary axis. So it's going to look something like that. Again, x prime, y prime is tangent to the ellipse, right? Something like that. So y prime minus x prime is perpendicular to the ellipse. And in that case, it's actually pointing out like that. So perpendicular vector here takes the derivative of y of t with respect to t, and you get minus 9r sine t. Oops, it's a plus because that was a cos. No, that's right. Derivative of cosine is minus sine plus r cosine t, and minus x prime would give me, let's actually make this minus y prime plus x prime. That would make this plus, this a minus, and the derivative of minus 2r cosine t becomes plus 2r sine t. And that's my perpendicular vector. So we'll take perpendicular dot f with x of t, y of t plugged in for x and y, and that would give us something. We want to show that that perpendicular dot f is always negative. And that means that f is always pointing to the inside of this ellipse, and you have to, once you cross that ellipse, you have to go in towards the origin. And so we can go back to our GeoGebra. And now we're looking at these ellipses up here. So there's my formula for my ellipse, right? And if we let our ellipse, our R value change, we get ellipses that look like that. And we want to show that if the radius is small enough, then the dot product between the vector field and the normal to that ellipse are, in fact, negative, and that once you go into the ellipse, you don't come out. So if we go back here, turn that off, and so here is the graph of this function, I hope. It's up here. So I must have actually used the inward pointing one when I'm looking at this one. So I use the inward pointing normal instead of the outward pointing normal. So for large R, you do get some places where the vector field is pointing out, right? But what we're worried about is as the radius of my ellipse shrinks, does it always have one side? And so when the radius gets small enough, so about 0.367, then what we're actually seeing is that that dot product is always positive. I think I'm using actually the inward pointing normal here instead of the outward pointing normal. I dropped a sign somewhere. And this is telling me that my solution curves always head into the ellipse. And as r gets smaller and smaller, the magnitude gets smaller and smaller. It starts heading down towards zero, but it's always above the axis. So what that shows us is that no matter what your what that shows us is that the solution curves that cross that ellipse, right, that cross these ellipses, they actually stay in the ellipse for all time, and then they have to end up going to the equilibria at B. So what does that tell us about what's going on here? Well, what we've found out is that, unsurprisingly, this equilibrium, we know it's a sink, but we can actually build ellipses where we can say it's definitely crossing in there. And that's one way to determine, are things sinks or sources, and in particular dealing with centers like we saw with the predator-prey. You could build circles around that and see whether or not things always stay in it or not. And that can tell you whether or not it's a center or a spiral sink or a spiral source. So if we're thinking about the two competing species, what we know is that there's an equilibrium here that's a sink. There's an equilibrium here that's also a sink. There's an equilibrium here that's a saddle. I'm not going to label it because I'm going to try and draw that. And there's an equilibrium here. There's a source, and I think it was 3,9 is a saddle. And what we know is if we take small circles around here, you have to go in there. And if you take a small ellipse around here, you have to go in that way. So if we think about these circles as being contour lines or level curves, if we want to build up a surface, right, we can also find circles here where everything has to go out, and the circles here where you're going in this way and out that way. So out that way, out that way. Okay, so now we're going to try and draw the picture now that we've sort of got what the should look like. If we're going to find an integral for this, which is really hard, and I'm not sure we can do it, it would have to have this kind of a shape. It would have to be going up here and up here, right? This would have to be some kind of valley, and the valleys would meet up here somewhere over that saddle, right? And so you'd be going down that way, and here you'd be now coming down this way, and also coming down that way. So it's very hard kind of to draw, but think of sort of the source is 0, 0, coming down this way, and the source sort of at infinity, coming down this way. And you have a saddle here, and you can drop down to one equilibrium there and drop down to one equilibrium there. right? And so that's what an integral or a Lyapunov function, even if you can't get an integral, maybe you could get a Lyapunov function, would have to look like um, to be able to track this kind of a solution. Okay, and so that brings us to the end of nonlinear systems.